Hello, this is Mr. White, and this video is on optimization, aka applied minimum maximum problems, part 2. Here are the 2 exercises for today. So apparently we want to find the point on this parabola, y equals x squared plus 1, that is closest in distance to the point with coordinates 3, 0. And step number 1 in the process tells us to identify given quantities, quantities to be determined, and to make a sketch when feasible, and we definitely want to do that here. So let's draw a reasonable sketch. Doesn't have to be super detailed, but just enough to get us the concept here. We know this graph of y equals x squared plus 1 is going to be a parabola that has been shifted up 1 from the origin, or its vertex will be 1 up from the origin. So if that's 1 right there, and then this be 1, 2, 3. And so this point at 3, 0 is going to be right here. And if I ask myself, where is the point on the parabola that is closest to that point at 3, 0? I'm asking, how can I minimize this red line segment that you see on the screen? Well, clearly I'm looking for a point that's somewhere in this neighborhood, right? So again, the purpose of sketch is to get us a sense of what we're dealing with and allow us to kind of document any variables we assign. So let's just state for the record, again, this point is at 3, 0. This point is at x, y. And the equation of this parabola is y equals x squared plus 1. And the quantity that we're really interested in is the length of that red line segment. So why don't we go ahead and call that L. And I'll do a little script L just so it's clearly not the number 1. And I'm going to call step number 1 complete. So step number 2 is where we write a primary equation for the quantity that is to be maximized or minimized. And in this case, minimized. So here, the quantity that we want to make as small as possible is that distance L. And we're going to use the distance formula, which I hope you recall is really just a form of the Pythagorean theorem. So let's ask ourselves, what is the rise in this case? The rise is going to be the y value, right? Or more specifically, y minus 0. So I'll take that leg of the triangle, square it. Now as far as the other leg of the triangle, the run, which we might call it, our sketch allows us to visualize and see that this x value is probably less than 3, almost certainly less than 3. So this length here is going to be 3 minus x. So 3 minus x, we'll square that. We're doing our a squared minus b squared equals c squared theorem. And I could square the left side. But since the length is what I want all by itself, it's the thing I want to maximize or minimize, I'm going to not square the left side. I'm going to square root the right side instead. So again, that's just an application of our distance formula or Pythagorean theorem. Okay, of course, pause if you need to take a moment to make sure that all makes sense to you. I'm going on to step 3 here. We take that primary equation, the thing that we want to minimize, and we want to reduce it to a single independent variable. In other words, we don't want it to have both an x and a y on this side. I don't care if it has just x, I don't care if it has just y. Either of those is fine, but it can't have both. So how convenient it is that we already have an equation that relates. We already have a secondary equation that relates the x and the y there. Remember, that's what we call a secondary equation, is one that allows us to relate these two and thereby get down to one variable. So here is our secondary equation. And if I plug it in to the primary equation, I'll get x squared plus 1 instead of writing out the y. I replace y with x squared plus 1, square that, and add it to 3 minus x quantity squared. And there is my primary equation written in terms of a single independent variable. All right, so step number 4, determine the feasible domain. As we're starting to pick up here, that step is one that often we can kind of afford to, if we forget, it won't be the end of the world. In this case, we're technically not constrained in any way. X can be any real number, positive or negative. Now we could tell from our sketch we expect it to be somewhere in that neighborhood, but technically X can be any real number, and this is the fancy way of saying X can be in the set of all real numbers. So we're on to step 5, familiar territory. We just need to minimize, using our calculus techniques, that quantity L. Now here's where a little bit of planning ahead can go a long way. When we look at this quantity, and we know that our next step is going to be to take the derivative and do critical numbers and such, we can see some ugly calculus coming up around the corner. We can tell that this function within another function, within another function, we can tell there's several chain rules coming up. It's going to be ugly. So here's what we can do to make our lives a little bit easier. If we really want to minimize L, if we want L to be as small as possible, if we want this quantity to be as small as possible, isn't that going to be achieved by making this quantity small as possible? So isn't minimizing the entire radical here going to yield us the same X values or the same critical numbers as we would get by simply minimizing the thing under the radical? That's the thinking, and that's a major point where if it doesn't make sense, please seek clarification on that, because that's how we're going to approach this, to at least make our calculus a little easier. Let's officially do this by squaring both sides of the equation, and that's something that I avoided doing earlier in the process, but now I'm realizing it's to my advantage to have both sides squared here. And again, the goal is, rather than minimize L itself, let's just minimize this L squared. And rather than continue to write L squared, I'm going to define another variable. I'm going to say let big L equal the little l squared. I'm not saying that's absolutely necessary. I just am choosing to do it that way. I would caution you with this, though, that anytime you define your own variables, you really do need to be explicitly clear what they mean. Okay, so let's continue with our goal here. We're trying to minimize big L now. So as far as taking the derivative, and is it worth distributing this out, foiling it all out, or just chain ruling it? I don't know. My experience tells me it's kind of even either way. So I'm just going to chain rule it, but you might try foiling it out if you prefer. So that's going to be 2x squared plus 1 to the 1 power times 2x with the chain rule plus 2, 3 minus x to the 1 power times negative 1 according to the chain rule. And if I distribute that all out and combine like terms, I'm going to get that. And I even have it in factored form there. Okay, let me acknowledge a mistake that I just noticed, and rather than redo the video, I'll acknowledge it. I put dl over dt. I should have put dl over dx or L prime. So let me fix that right here. So what happens when you talk and do math at the same time. So we're running into a problem that's a little bit unusual for this class, although it's certainly not unusual for real life. And that is that we have an equation that we need to solve, an algebraic equation that we need to solve, and it doesn't look like it's going to factor cleanly. Sometimes we get a little bit lucky with cubic equations. Sometimes we can factor them easily, but this one isn't going to. So what that really means for us is that we're going to use the calculator here. Technically, there are some calculus techniques one could use to come up with an approximation for x, but for the scope of this class, we're just going to use our calculator. So here is the equation. Now remember, this represents L prime, or dl over dx. I know from our earlier sketch up here that we're expecting a number that's fairly small. So I'm just going to go to zoom decimal. Zoom and then press the number 4. And this isn't the best view of the graph as far as seeing what the entire function looks like, but I only care about that x-intercept at 0. And I can tell visually that it's between 0 and 1. So let's go to second calc, and we'll go to option number 2 there, 0, to find the x-intercept. And for left bound, I'll type in 0. For right bound, I could type in 1, but I'm going to type in 2 just to be safe. So I just typed in 2 and then hit enter. For guess, I'll just hit enter. And there is my x-intercept. So that is going to be our critical number. Now I have to admit, if it feels a little bit cheap using the calculator, I kind of agree with you, because if we're going to allow ourselves to use the graphing calculator, why didn't we just do calc min or calc max a couple steps ago? Valid question that I don't have a great answer for, other than that we want to learn the ideas of calculus, even if we have to cheat once in a while and use the calculator. So this is the critical number that we were expecting to be a rather small positive number. So approximately equal to 0.735. To find what the corresponding y value is, I'm going to go to second quit. And remember, the last x value that the calculator displayed is still remembered by the calculator. So I'll type x squared plus 1. That's our function that we're dealing with, right? That's our parabola. And that is going to be my y value. Okay, so if x is about 0.735, then y is going to be about 1.540. Again, going by the AP rule of 3 decimal places. Let's put a box around that. Again, I've mentioned this before. We're allowing ourselves to be a little bit lax about completely doing the first or second derivative test. We're using a little logic to say, I know that's a minimum. Just our picture, it's quite obvious from our picture up above here that that's going to be a minimum, and that this length will only get longer as you go to different points on that parabola. So we will call that one done. The one last thing I'll do is bring up the GeoGebra model. We see here the optimal point there in black or dark gray. We see the length of the line segment, or the distance between the 2 points we're interested in, being displayed there. And we see that right when I get at that optimal point, the length is 2.739-ish. If I go to the left, that length gets bigger. If I go to the right, that length gets bigger. So it looks convincing that we found our optimal point. All right, let's go on to the next one. So I'm designing a detention chamber for these 6 troublemakers. And I want each of them, I'm generous enough to give each of them 20 square feet of floor area in their individual chambers. And we want to know what are the dimensions of each cell if I want to minimize the total length of the walls. In other words, I want to minimize the total length of all those blue line segments you see on the screen right now. So again, let's conceptualize this in GeoGebra. Here is one extreme, or at least almost extreme case, where each of the cells is 20 square feet because it's 1 foot by 20 foot. But we can tell that those vertical lengths, those vertical walls, are going to be rather long, much longer than they probably need to be. And all I need to do is take that 1 foot measurement and change it to 2 feet. And I maintain my 20 square feet each. It's 2 by 10 now, but it sure drastically reduced the length of those vertical line segments. And if I keep on going, let's say I go out to 4 feet, or 4 by 5 for each individual cell. That looks pretty reasonable. I could go to 5 by 4. That also looks reasonable. But as I go to the other extreme, now the horizontal walls are going to be such that the total wall length will be certainly not optimal. So while we're in the design phase, let's get rid of these little rapscallions. And we can count this as our sketch. That is required for step 1, right? Identify all the given quantities to be determined, and when feasible, make a sketch. So I'm going to call each of those horizontal line segments W. W for width, and I'll call the vertical ones H. And I'll just document in the picture there that each of these cells is going to be 20 square feet. And now we'll go on to step 2, writing that primary equation for the quantity that is to be maximized or minimized. So I'm going to use the letter P, I guess for perimeter, although that's a little bit dangerous because that seems to imply that perimeter is just the total length around. I obviously want all those wall lengths, but I'll use P anyway for lack of a other preferable choice. And having said that, be careful. I have had a number of students in the past just focus on the perimeter and for whatever reason forget these interior walls. So let's ask ourselves, how many little wall segments of length W do I have? Well, there's clearly 1, 2, 3 here, 4, 5, 6, 7, 8, 9, right? So we have 9 of length W, and then 1, 2, 3, 4, 5, 6, 7, 8 of length H. Add them together, and that gives me this total wall length. So that was step 2. That's the quantity that we want to minimize in this case. Step 3 is where we reduce that to a single independent variable. We don't want it in terms of both W and H. We don't care which one, but we need to get it down to one of those, one or the other. And so here's where our secondary equation comes in. W and H are related to each other by this 20 square feet. So W times H equals 20, or what will suit us better is to get one of those two by themselves. And again, it really makes absolutely no difference. I'm just going to very arbitrarily say W equals 20 over H instead of H equals 20 over W. We will combine those primary and secondary and get P equals 9 instead of times W, 20 over H plus 8H. Which, if I simplify it and write it in a little bit more calculus-friendly terms, will be 180 H to the negative 1 plus 8H. And I've completed step 3. I've now got this primary equation in terms of just a single independent variable, H. As far as the feasible domain of this primary equation, well, we're dealing with a physical pen here, so H better be greater than 0. And now we're on to the last step, using our calculus techniques to minimize this function P in this case. So let's figure out P prime. P prime equals, I'm looking over here and I'm going to get negative 180 H to the negative 2 plus just 8. And we'll set that equal to 0 or undefined. I know that undefined never seems to yield anything useful, and I'll admit, in optimization problems, I'm not sure if I've ever seen the undefined yield anything useful, but we should still write it just to stay in practice. Okay, so let's simplify a bit here. We've got negative 180 over H squared plus, let's do common denominators, 8H squared over H squared equals 0. And just as I was saying, undefined is only going to occur when H is equal to 0, which we said is not within the feasible domain. Doesn't make sense for H to be 0. So we acknowledge the undefined, but then cross it out. Might as well at this point multiply both sides by H squared just to handle that denominator. And that will give us negative 180 plus 8H squared equals 0. And that is going to give us H squared equals, let's say 90 over 4. Now notice I reduced the 180 over 8 down to 90 over 4, but I didn't reduce it all the way to 45 over 2. Can you see why? Scroll down a bit. The reason is because I anticipated that my next step was going to be to square root. And I like having a perfect square on the denominator. So when I square root, I get, see, 3 root 10, that's the square root of 90, right? Over 2. And technically, just to make a point here, technically this is a solution to this equation. But remember, negative values of h are not in the feasible domain. They don't make sense, so we'll acknowledge it and then cross it out. So again, do we have to do the whole first or second derivative test? I'm going to be a little bit permissive and say no. We used our earlier logic that we know that super tall and skinny configurations here aren't going to do us any good. Likewise, really long but short configurations don't do us any good. We can convince ourselves that either of those extremes is only going to serve to make the total fence length really large, and therefore this is going to give us a minimum value, not a maximum. So if you have any question about what you can or cannot assume, please get that clarified. Let's remind ourselves that we need to find the other dimension. So if I go back up to where I had w expressed in terms of h, I just have to take that h value and divide it into 20, and that will give me my w. And there it is. And we are only asked for the dimension of each cell, so technically we're done. There's the width and the height. Actually, I should go ahead and put the units in there. And often for these sort of real-world-ish type problems too, those are cases where I think our decimal answers may be more appropriate. There they are, and since we're having so much fun, let's go ahead and figure out the total perimeter needed here as well. Or total wall length, I should say.